For a very long time, people looked up at the stars. They wanted to know where they fit in the big, wide sky. They drew pictures of star groups and followed the paths of planets. They thought they were starting to understand how the whole universe worked. But in the last 50 years, something amazing happened. The picture of the universe we had was broken. It was redrawn. And it turned out the universe was much, much bigger, stranger, and more mysterious than anyone had ever guessed. This story isn't just about new stars and far-off places. It's about a big change in how we understand things. This change is caused by things we cannot see, but they shape everything we know. Think about the universe as we thought of it only a short time ago. It was made of stars, planets, gas, and dust. All of it was pulled by gravity, which we understood. We thought we knew what it was made of, how big it was, and where it was going. Then, discoveries came that changed everything we thought we knew about the universe. We sent out space explorers like Voyager, which went past our sun's family of planets. They showed us our home planet as a tiny blue dot. This made us feel small. We found thousands of planets going around other stars. This proved our sun's family of planets isn't special. There might be billions or even trillions of other worlds. The number of star groups, called galaxies, was thought to be in the millions. But telescopes like Hubble showed us there are hundreds of billions, maybe even trillions. The universe wasn't just big, it was too big to even imagine. But the biggest surprises weren't about what we could see. They were about what we couldn't see. Near the end of the 1900s, scientists like Vera Rubin noticed something strange. Galaxies were spinning too fast for the amount of stuff we could see in them. Stars on the outside edges should have flown away into space. But they stayed put. This led to a new idea. There must be something invisible, like a hidden structure, holding these galaxies together. We called this dark matter. And there's a lot of it. Scientists now think dark matter makes up about 27% of everything in the universe. That's 5 times more than all the stars, planets, gas, and dust we can see. We don't know what it is. It doesn't shine or reflect light, so we can't see it. It's not made of the same tiny pieces as us. It's a very important part of the universe, needed for us to exist, but it's completely different from us. Scientists are working very hard. They are building special machines deep under the ground to try and find even a little bit of this hidden stuff. They hope to finally learn what it truly is. But the universe still had more. 1. The changing universe. For a long time, we thought we knew the universe well. We looked up and saw stars, faraway star groups called galaxies, and planets. We understood how things fall, called gravity, and the powers that move things. It felt like we could handle it. It seemed like we knew what would happen. We had a plan for the universe, and we were carefully adding the small details. We thought the universe was made of the things we could see, like the tiny bits called atoms that make up everything around us. We believed we were close to knowing what it was made of for sure and what would happen to it. In the end. Then, things started to change. It wasn't a big, sudden shake, but small movements that began to make us question what we thought we knew. These small movements started quietly, almost too small to notice, but they grew. They showed us a universe that was much bigger, stranger, and more mysterious than we had ever imagined. In just a few years, our idea of the universe has changed completely. This happened because of amazing discoveries that showed us hidden powers that control everything. Think about the Voyager spaceships. They were sent out in the late 1970s to explore the planets far from us. But they kept going and going. They traveled past the edges of our sun's family of planets. They carried something very special with them, a message, a picture of our home. When Voyager 1 looked back from the huge empty space between stars, it took a picture that changed how we saw things. It showed Earth, a very small, light blue dot, floating in a giant space ocean. This was not just a pretty picture. It was a powerful way to show us how big things are. It showed us that our sun's family of planets, which feels like our neighborhood, was just a tiny speck in a space too big to measure. This was an early sign that the universe was much, much bigger than our old maps showed. It also showed that the empty space between things was as important as the things themselves. And then we found exoplanets. For many years, we wondered if we were the only living things. Was our sun's family of planets special? Were there other worlds going around other stars? For a long time, we could only hope so. But in the 1990s, our telescopes started to find them. First one, then another, then a few, and then many. Now, we know about thousands of exoplanets. These are worlds going around stars that are very, very far away. Some are big gas planets, and others are rocky like Earth. This discovery did not just add a few more points to our map of the universe. It changed how we think about how planets form and where we fit in the universe. It showed us that planets are not rare. They are found everywhere. The universe, it turns out, is full of worlds. The idea that our sun's family of planets was special, one of a kind, disappeared. We went from knowing about no planets outside our sun's family to realizing they are very common. Some people think there are more planets than stars. But the huge size of the universe was not just about single planets or even our own star group. The Hubble Space Telescope, which was sent up in 1990, gave us a new way to see deep into space. In its famous pictures of the deep field, Hubble looked at a part of the sky that seemed empty for days. What it showed was amazing. It found thousands and thousands of star groups, called galaxies. Each galaxy has billions of stars. They were all packed into that small dark space. It was like looking into a space ocean, and we realized our small area, our Milky Way, was just one drop in that huge, shining space. The universe was not just big, it was unbelievably huge. It had so many galaxies that it was hard to count, all connected like a big web. Our old ideas about how much stuff was in the universe were suddenly too small. As these discoveries showed us a much bigger universe, a new puzzle started to appear. This puzzle pointed to something even more important. The universe was not just big, but it was also held together. In a strange way, scientists looking at galaxies noticed something odd. The stars on the outside edges of these galaxies were moving around their centers much too fast. Based on the stuff we could see, the stars, gas, and dust, these galaxies should have broken apart. The pull of gravity from the visible stuff was not strong enough to keep everything together. It was like the outer stars were being held by an invisible hand. This was a very important moment. Scientists like Vera Rubin, who carefully studied how galaxies spin in the 1970s, started to suggest that there must be more to galaxies than what we can see. They thought there was an invisible substance. This substance had gravity, but it did not give off, soak up, or bounce light. They said this unseen part must make up most of a galaxy's weight. We could not see it, we could not touch it, but its pull of gravity was clear. It was the missing piece of the universe puzzle, the invisible support holding galaxies together. This was the first idea of dark matter. We started to understand that the universe was not just made of stars and planets. It was mostly controlled by something we could not see. This unseen thing held the parts of galaxies together. This new idea was a huge change. It meant that the familiar, visible stuff that makes up everything we can see and touch, from us too, the farthest star, is only a small part of all the stuff in the universe. Most of the universe's matter, it turned out, was invisible. It was like a ghost whose gravity shaped the universe. This challenge to what we thought we knew about what the universe is made of was just the start of many new discoveries. As we tried to understand this unseen matter, an even more surprising power was waiting in the universe. This power would change how we think about what will happen to the universe in the end. 2. Space exploration discoveries. 50 years ago, we thought we knew a lot about space. We knew our sun and its planets. We knew our home galaxy. But then we started to really look. We used amazing tools to see farther. What we found changed everything we thought we knew about space. Think about the Voyager spaceships. They were sent out a long time ago, in the 1970s. They were our first real explorers of the outer planets and beyond. They showed us Jupiter, Saturn, Uranus, and Neptune up close. Before, we only saw them as tiny dots through telescopes. Voyager sent back amazing pictures. They showed big storms, beautiful rings, and moons with their own unique stories. But perhaps the most important thing Voyager did was on its long trip into deep space. From very, very far away, it turned its camera back at Earth. It took a picture called the pale blue dot. Imagine our whole world, all of human history, every good and bad thing, shown as one tiny speck of light. In a huge, dark space. It made us feel small. It showed us how alone and delicate our planet is in the big universe. These trips didn't just show us faraway places, they showed us how incredibly huge the universe is. And that size? It just kept getting bigger. For a very long time, we thought our solar system was the only place with planets. We thought planets were rare. But then we started finding planets around other stars. We used very sensitive tools on Earth and in space to find them. At first, we found only a few. Then, we found many. Spaceships like Kepler and TESS have found thousands of planets around other stars. Thousands. And we keep finding more. There are planets of all sizes and types. Some are very hot and made of gas. Some are rocky and bigger than Earth. Some might always have one side facing their star. This means that if planets are so common, then places where life could exist might be all over the galaxy. And the universe. It's not a question of if there are other worlds, but how many and what they are like. But space is not just about planets. It's about galaxies. Galaxies are huge collections of stars, gas, and dust. For a long time, our telescopes could only see so much. Then, in 1995, the Hubble telescope did something amazing. It looked at a tiny piece of the sky, smaller than a grain of sand held at arm's length. It looked for 10 days. What it saw was a picture with thousands of galaxies. Some of these galaxies were seen as they were more than 10 billion years ago. This was a huge surprise. Suddenly, we weren't looking at a few hundred galaxies, we were looking at hundreds of billions. Later, even deeper pictures showed even more galaxies in that same tiny spot. This showed that the universe is full of galaxies, and each galaxy has billions or even trillions of stars. The number of galaxies alone tells us there is a lot of stuff in the universe. But when we looked at how these galaxies moved and interacted, we found a puzzle. Look at how galaxies spin. We can measure how fast stars move around the center of a galaxy. Based on the stars, gas, and dust we can see, we expect stars farther away to move slower. This is like planets farther from the sun moving slower. But that's not what we see. Stars on the outside of galaxies move just as fast, or even faster, than stars closer to the center. This means there is much more mass there than we can see with our telescopes. It's like the galaxy is surrounded by a big, invisible cloud of stuff. This stuff has extra gravity that keeps the outer stars moving so fast. We call this invisible stuff dark matter. We can't see it. It doesn't give off light, or block light, or bounce light. But its gravity is very strong. It holds these big galaxies together. This isn't just happening in galaxies. When we look at groups of galaxies, which are huge collections of hundreds or thousands of galaxies held together by gravity, we see the same problem. The stuff we can see in these groups doesn't have enough gravity to keep them from flying apart. Also, when light from faraway things passes by these groups, gravity bends the light. This is called gravitational lensing. It happens because mass bends space. By seeing how much the light bends, we can guess how much mass is in the group. Every time, these guesses show much more mass than all the visible galaxies and hot gas combined. This missing mass strongly suggests that dark matter is there. It's like an invisible frame that helps build and shape the universe. Without it, galaxies and galaxy groups as we know them would not exist. But the universe has more mysteries than just unseen mass. There's an even stranger force that is controlling the future of the universe. For a long time, scientists thought that the universe, which started with the Big Bang, was slowing down because of gravity. This made sense. But in the late 1990s, two groups of scientists studying exploding stars found something different. They were expecting to see the universe slowing down. Instead, they saw the opposite. The universe is not slowing down, it's speeding up. It's expanding faster and faster. This discovery was so surprising that the scientists who found it won a Nobel Prize. What could be causing this faster expansion? It needs a force that pushes things apart, working against gravity. This mysterious thing is called dark energy. Unlike dark matter, which gathers in clumps and pulls things together with gravity, dark energy seems to be spread out everywhere in space. It pushes things apart. It's like there's a hidden energy in space itself that makes it stretch and expand faster and faster. Dark matter makes up about 27% of the universe. Dark energy makes up a huge 68%. This means that the stuff we can see, stars, planets, galaxies, us, is less than 5% of everything that exists. These discoveries from exploring space, from the Voyager ships to the Hubble telescope and the search for planets around other stars, have completely changed how we see things. They have shown us a universe that is much bigger, much more complicated, and much more mysterious than we ever thought. We used to think about our place in our solar system. Now we are thinking about billions of galaxies and forces we can't see or touch. These discoveries are not just about finding out more, they're about finding out what reality is made of and the unseen forces that control the universe. It turns out the universe is not just what we see, it's also what we don't see. And these unseen parts, dark matter and dark energy, are now very important in our effort to understand how the universe works and where it is going. 3. The role of black holes. For a long time, we looked into the dark, trying to find answers to the biggest questions about space. Now, we will learn how the most powerful things in space, black holes, are not just like vacuum cleaners, but are very important in the big story of dark matter and dark energy. Most star groups, like our own Milky Way, have a big secret hidden at their center. It is not a bright star or a cloud where new stars are born. Instead, it is a super big black hole. These are not just strange ideas, they're the strong pull that makes whole star groups spin around them. Think of a giant spin in space, so heavy, so strong, that nothing, not even light, can get away. These are the centers of powerful star groups, and knowing about them is key to understanding space. Think about our own Milky Way. At its middle is Sagittarius A, a super big black hole that weighs as much as 4 million suns. Its pull is huge, making stars and gas clouds spin around it very fast. We see stars moving around this unseen center so fast that it does not make sense if only the things we can see were there. They are moving too quickly, too strangely. This fast movement is one of the best signs that these strange objects exist. The huge pull needed to keep these stars in their spinning paths can only be explained by something very heavy and dense, packed into a tiny spot, a black hole. Now, let's connect this to the invisible things in space. While black holes are made from matter that has fallen in, their strong pull helps us guess where dark matter is and how it is spread out. Dark matter, as we know it, is invisible stuff that makes up most of the things in space. We cannot see it, but we know it is there because its pull holds star groups together. Our ideas about how fast stars move at different distances from the center of a star group show a big difference. Stars far away move much faster than they should if only the visible matter was there. This means there is unseen stuff, a big cloud of dark matter around the star group. This is where super big black holes become important in this space mystery. Their own huge pull is a big part of what happens in the center of a star group. When we study how stars and gas move near the center of a star group, we must think about the black hole's pull. If we do not carefully count the pull of Sagittarius A, our measurements of the stars moving around it would be wrong. This mistake would then lead to wrong ideas about where dark matter is. By carefully counting the black hole's pull, we can then see and better understand the pull of the dark matter cloud around it. It is like trying to understand the wind by first thinking about the trees it blows through. The black hole is a big, visible, because of its pull, thing that helps us see the invisible better. It helps us draw a map of the pull in space more clearly, letting us better see the shape of the unseen dark matter that holds star groups together. Also, these giant things in space do more than just pull things in. They help build their star group homes. When a super big black hole eats, pulling in gas, dust, and even stars, it does not just disappear. This can cause very strong events. As matter spins inward, it forms a disk, getting very hot and sending out a lot of light. In many cases, this eating also sends out strong streams of hot gas, moving almost as fast as light away from the black hole. These huge streams can reach very far, much farther than the visible parts of the star group. They push through the gas in the star group, making big empty spaces. This sending out of energy and matter greatly affects the star group itself. It can heat up the gas, stopping it from cooling down and making new stars. This feedback is a very important way that star formation in star groups is controlled. Without these energetic outflows from super big black holes, star groups might make stars too quickly, using up their gas, and having no more potential to make stars later. This control is not just about making stars nearby, it is about how the whole star group grows and fits into the larger universe. The very shape and size of star groups, the types of stars they have, and the amount of gas they contain are all affected by the active part these black holes play. This active effect, this shaping of the areas around star groups, also connects to the bigger picture of space. How star groups are spread out in the universe is not random. They are in long lines and groups with huge empty spaces between them, making what we call the cosmic web. This large-scale shape is a direct result of the push and pull between dark matter and dark energy. Dark matter provides the structure, pulling in normal matter to form these shapes. Dark energy, on the other hand, pushes things apart, making the universe expand faster and pushing these shapes further away from each other. While super big black holes are not directly causing dark energy, their part in how star groups grow means they are involved in the big story told by these unseen forces. The very being and growing of star groups, which are the large shapes affected by dark matter and dark energy, are tied to the actions of their center black holes. The way star groups join together, pull in matter, and grow are all affected by these giant gravitational things. And the larger expansion of space, pushed by dark energy, decides how fast star groups move apart and the environments where these black holes and their star groups exist and grow. So, when we look at a star group, we are not just seeing a collection of stars and gas. We are seeing a complex system where a super big black hole at its center acts as a strong gravitational anchor, a controller of star making, and a key part of the puzzle that helps us understand the invisible dark matter clouds around it. These extreme objects, made from collapsed stars, are not just strange things in space, they are essential to the structure, growth, and movement of the universe as we see it, indirectly connecting us to the unseen forces that guide our universe. But as we look closer at the spinning dance of star groups, we find an even bigger mystery, a force that stretches across space, deciding its final end. A force that makes up most of our universe, yet stays completely unseen. 4. The future of exploration. We have looked into the dark of space and seen the hidden forces that shape everything. We have found more questions than answers. What happens next? Where do we go to learn more about the universe? Our journey to learn is not finished. It is speeding up into an exciting new part. What we know now about dark matter and dark energy is just a small picture. The universe has many more secrets. We are building tools to find them. This is the future of exploring space. For a long time, we used our eyes and then telescopes to see the universe. But space is huge. The quiet signals of dark matter and dark energy need very strong and exact tools. This is where the new observatories come in. Think of them as super eyes for space. They will show us the universe in amazing detail, like in science fiction stories. The Vera C. Rubin Observatory is one of these big tools. It is high up in the mountains of Chile. Its giant mirror and wide view will let it look at the whole sky every few nights. This means it will create a lot of information. It will make the most detailed 3D map of the universe ever. This map will show us how galaxies are spread out. It will show how dark matters pull bends light. It will track how the universe is growing with great care. Every galaxy, every group of galaxies, every small bending of light will be seen. This will help us learn for many years. Then there is the Nancy Grace Roman Space Telescope. This mission is made to answer big questions about the universe. It will study dark energy and how heavy tiny particles called neutrinos are. Its wide view will let it look at big parts of the sky. It will search for signs of dark matter and dark energy. It will watch stars explode. This will help it measure how fast the universe is growing over time. It will also map dark matter using how its gravity bends light. This is like the Rubin Observatory, but in space, away from Earth's air. These observatories are not just bigger, they are smarter. They use new tools and smart computer programs. These help them look through all the information. They find the small signals that tell us about the invisible structure of the universe. They are built to find the hidden clues that will help us know what dark matter is. They will help us know how dark energy is guiding the end of the universe. But telescopes only show us what these hidden forces do. They show how dark matter holds galaxies together. They show how dark energy pushes the universe apart. To truly understand them, some scientists are trying a different way. They want to catch a dark matter particle in action. This is where particle physics and underground labs are important. Imagine a very sensitive tool. It is deep under the ground, safe from space rays. Why underground? To block out all other signals. This leaves only the faintest possible signs from a dark matter particle. Experiments like XENONNT in Italy or LZ in South Dakota are leading this search. They use big tanks of very pure liquid xenon. This is kept very cold. If a dark matter particle, like a WIMP, goes through this tool, it might bump into a xenon atom. This bump would make a tiny flash of light and a few electrons. The tools are so good they can see these small events. They can tell them apart from other noise. This is very hard, like trying to hear a whisper in a storm. But finding dark matter particles would be a huge reward. If we can find these particles, we can learn their weight, how they interact, and what they are like. This will help us understand the biggest part of matter in the universe. The search is not just for WIMPs. Scientists are looking at many other ideas. Some are very light particles called axions. Others are even stranger. New experiments are being made to look for these. They are pushing the limits of what we can see. This search for direct proof, along with the big surveys from new telescopes, works together. One set of studies tells us where dark matter and dark energy are and what they do. The other tries to tell us what they're made of. Now, let's talk about something exciting for scientists, the Hubble tension. For many years, we have measured how fast the universe is growing. We do this in two main ways. One looks at the early universe using light from a long time ago. The other looks at the universe now, using how far away stars and other things are. Here is the problem. These two ways do not match when we use our best ideas. The early universe suggests it is growing faster than the universe now. It is like looking at a map of a city from different times and seeing the distance between two places. Is very different. This is not a small difference, it is a big one. It means something important might be missing from our idea of the universe. This difference is not a mistake, it is a clue. It points to new science. Our current idea of the universe, called the lambda CDM model, has worked very well. But this difference suggests it might not be complete. The lambda means dark energy. CDM means cold dark matter. If the universe is growing at a different speed than we thought, it could mean dark energy has changed over time. Or it could mean dark matter has features we do not know about. Or maybe there is a new force or particle. Scientists are working hard to fix this problem. They are making their measurements better. They are finding new ways to measure. They are looking at different ideas. The Roman Space Telescope, which can measure stars exploding far away, will be very important for measuring how fast the universe is growing now. Future missions will give even more exact measurements of light from the early universe. Solving the Hubble tension will be a big moment. It could change how we understand dark matter, dark energy, and space itself. It shows how science works. When what we see does not fit what we think, it is not an end, but a chance to explore new places. This future exploration is not just about single parts. It is about mapping the whole universe. Imagine the universe not as separate stars and galaxies, but as a huge connected web. This web has strands where galaxies and clusters of galaxies are found. There are big empty spaces between them. What makes this web? Dark matter. It is the strong frame that holds everything together. Future studies, like those from the Rubin Observatory and the Roman Space Telescope, will map this web in amazing 3D detail. They will measure where billions of galaxies are. They will show how dark matter's pull bends space. By seeing how this web has changed over time, scientists can test different ideas about dark matter and dark energy. They can see how dark energy is stretching these strands. They can see how dark matter's pull has guided their shape. This detailed map helps us measure very carefully how the universe has grown over time. By studying how galaxies gather together and how light bends as it travels across billions of miles, we can guess where dark matter is. The more detailed our map, the more we can learn about dark matter and dark energy. Are they always the same, or do they change? Do they affect each other? These are questions this mapping will help answer. It is like going from a blurry drawing of a city to a clear map showing every building. Every detail is important. Every detail can lead to new ideas. Beyond our nearby space, future exploration also looks to the very edge of what we can see and even further. Plans are being made for tools that will go farther than ever before. They will not just study planets and stars, but the basic rules that shape the universe on the biggest scales. These big plans, which might be decades away, are part of our endless need to learn. They show our deep wish to explore and understand our place in the universe. The tools being made now for mapping dark matter and dark energy are the first steps for these even bigger future journeys. These big missions and new experiments are not just about collecting information. They're about asking new questions. Questions we cannot even imagine today. The universe always surprises us. The biggest mysteries might still be waiting to be found. Conclusion. For 50 years, we have learned so much about the big, wide universe. At first, it seemed simple. We saw stars, planets, and big groups of stars called galaxies. But the universe had surprises. What we can see is only a small part of a much bigger, amazing picture. Our idea of what is real has changed a lot. The universe is much bigger, stranger, and more mysterious than we ever thought. What is most amazing is that it is shaped by forces we cannot see. We started by looking at things we know, like light from far-off stars. But the numbers did not make sense. For example, a smart scientist named Vera Rubin found that stars and galaxies were moving too fast. They should have flown away. Something we could not see, something with a lot of pulling power, was holding them. This is called dark matter. It is like invisible support, holding galaxies together. It is the glue of the universe. It is not just a little bit of extra stuff. It is more than 80% of all the matter in the universe. We do not know exactly what it is. It could be tiny particles we cannot see, but we know it pulls things together. It is the unseen builder of the universe's shape. But the universe had more secrets. When we looked even farther away and further back in time, we found another, even bigger puzzle. We learned that the universe is not just getting bigger, it is getting bigger faster and faster. Gravity, which we thought would pull everything back together, is not strong enough. This is because of dark energy. It is a power that is everywhere in space. It pushes galaxies apart more and more quickly. It is the biggest part of our universe, making up almost 70% of all its energy. What is it? We do not have a clear answer. It is a power that makes us question our basic ideas about how things work. It is a mystery that is changing the future of everything. These are not just separate facts. They are part of how the universe works. Dark matter and dark energy are not just ideas. They are the main reasons why the universe has changed over time. Without dark matter, galaxies would not have formed the way they did. Without dark energy, the universe would be shrinking, not growing into the